Today, let's prove the formula for finding the angle between two vectors. So that is the angle theta is equal to inverse cosine of the dot product of these two vectors divided by the product of the magnitudes of these two vectors. And let's just do the 2D case. Because for the 3D case, we'll just have one more component. The computation, the idea, is the same. So here we go. Proof. I'm going to start off by saying that the vector u, b, u1, u2 in the component form, and then v is equal to v1, v2. And let me just show you guys a picture. Let's say u looks like this, and let's say v looks like this. And the angle between them is defined to be right here. The angle has to be between 0 to 180 degrees, or in radians it will be 0 to pi. So it's not the big one, it's this one. Here is what we have. Why don't we connect from here to here so we have a triangle to work with? And because I went this way, this side we can write it as u minus v. And just to review why, here is a quick idea. So we have v, and then this is u. Negative v means that we just turn this to the other way, right? So we have negative v here. And then this is vector u. We can move it down here. So this right here is still u. And then we can move this to here. This is negative v. Now we can combine u and negative v together by doing the parallelogram method. That means you go from here to here. Right? This is u minus v. And finally, you can move this back here. So this is exactly what we have, and that's u minus v. Now, we have all three sides and one angle. We can use law of cosine, and that's the key for this proof. So we can say the length of this side, so we'll take the magnitude, so u minus v, and then square that is equal to take the magnitude of this and square, and then add it with the magnitude of this and then squared. So u magnitude square that, and then likewise do this. And then minus, because this is not necessarily a right triangle. So minus 2 times the magnitude of this and that times cosine of the angle between them. And this is because of law of cosine. So you can see the cosine and the inverse cosine here, and you can see this and that match, right? So now, to finish the proof, all we have to do is just a bunch of computations. We are going to turn this into the component forms and then just do the work. So I will do it on the side for you guys. Let's figure this out first. U minus v, this thing is equal to, let's look at the component form, just this minus that and this minus that. So this is equal to u1 minus u2, and then u1 minus v1, and then u2 minus v2. And then we have to get the magnitude, right? So just take the magnitude of this, take the magnitude of that. That means we take the square root, square the first component, so it's u1 minus v1, square that, and we add this thing squared. Well, we have to have the square on the outside too. So it's this thing squared, and this is being squared. So in fact, it's the whole thing right here, and we have to square that. So the square and the square root cancel. We just have the inside. Multiply this out. Square this, so u1 squared minus 2 times this and that, plus this thing squared. And then do the same thing here. u2 squared minus 2 u2 v2 plus v2 squared. And that's the most that we can have, huh? Oh, sorry, this should be a 1. Okay, so that's on the left hand side. And you can pretty much guess that we pretty much just do the same for this and that. But I will put this right here for the left hand side. So we have u1, I'm just going to copy that down, u1 square. Let's fast forward a little bit. Alright, so this is what we have. Now, for this, all we have to do is u1 square plus u2 square. So u1 square plus u2 square, because it's the magnitude square, the square root and then the square cancel, and then just this. Similarly, we have v1 square plus v2 square, and the rest is the same. So minus 2 magnitude of u, magnitude of v, cosine theta. Now we can see that both sides have u1 squared. That is so nice. They cancel out. And we also have v1 squared. Oh, also this and also this cancel out. And then this and this cancel out. And then finally, just do this, and then we have that. Yeah? And, okay. Let me just write this down again. So this right here is negative 2 u1 v1 minus 2 u2 v2 equals just this now. Negative 2 magnitude of u times the magnitude of v times cosine theta. And of course, we can divide everybody by negative 2. So we just have u1 times v1 plus u2 times v2, and that is equal to this part, which is the magnitude of u times the magnitude of v times cosine theta. This is what? It's precisely our dot product. So we can just turn this into the dot product notation. This is u dot v. And imagine if you want to do it with the 3D version, you just have one more term with u3 times v3. Told you it's going to be the same thing, just longer. Anyway though, that's pretty much it, because at the end, we just have to divide this on both sides and then take the inverse on both sides. So I will just write this down one more time. Cosine theta equals u dot v divided by the product of their magnitudes. And then finally, just take the inverse cosine on both sides. The angle theta is equal to inverse cosine of u dot v divided by the product of their magnitudes. And that's it. Okay, two things I want to mention before we go. First, the range for inverse cosine is from 0 to pi, which is perfect because we do not want our angle to be negative, and we also do not want our angle to be bigger than pi. Now the second thing is, I'll write this down. If, when we do the dot product of u and v, and we end up with 0, then we will know that these two factors are perpendicular. And to see why, here we have the formula. We know the angle between them will be inverse cosine of, if u dot v is equal to 0, the whole thing inside is equal to 0. And now, what's inverse cosine of 0? In another word, cosine of what angle will give us 0? The answer for that is 90 degrees, which is pi over 2. Okay? And here's one small thing. Perpendicular makes sense when you're talking about 2D factors or maybe 3D factors, but later on, once you get into like higher dimensions, you cannot really draw pictures for like 4-dimensional factors and all that. So there's another word that we use for this right here as well, and that is orthogonal. And of course, you can also say that they are normal, but if you want to see the difference between perpendicular, orthogonal, and normal, you can check out my other video for that. But for now, this is it.